I thank the organizers for inviting me to deliver this plenary lecture. Considering interdisciplinary nature of this lecture and also diverse background of the audience, I will briefly give some overview on chirality, plasmonics, and superlattices before moving into specific examples. In 1904, Lord Kelvin proposed that any object, figures, or geometrical shape is chiral provided it has non-superimposable mirror image. Today, we know that chiral objects are ubiquitous in nature and they are important in understanding the origin of life and evolution of life. In biological system, we encounter chirality at molecular and macromolecular scale. At molecular scale, they're fundamentally important as an example shown here of limonene. Depending on the enantiomers, it can differ in the flavor and the taste. At the drug discovery level, they're even more important as a wrong enantiomer can lead to opposite effect. Thalidomide is one of the examples where one R thalidomide has the sedative effect, whereas the S form is as the teratogenic effect. Teratogenic effect is abnormal fetal development. In 1950s, it was recommended for women having morning sickness. As many of you might know, that eventually it ended up the death of massive number of children, and also those kids were born with the deformed limb. Going beyond molecular level, at macromolecular level, in biological system, we find alpha helix proteins and DNA double helix, and even macroscopic object in plants, you can find the tendrils. All these are helical structure. And of course, chirality doesn't mean that only helical structure. We can also find other forms of structures. I refer in this lecture helical structure because at the end, the examples that I'm going to give you are also dealing with the helical colloidal level structures. Beyond molecular level, that is at supramolecular level, we can also find chirality, and that is called amplification chirality. It's a process of self-assembled small chiral molecule into higher order structure, which can be visualized, for example, in microscopic image. And one simple example here is a tartarate. If you take tartarate and treat it with a Gemini surfactant, a cationic surfactant, and depending on the enantiomer, you will have either right-handed helix or left-handed helix. And such structures can be used to make a templated silica helical structures. And eventually, after coating silica, these organic structures can be burned. So you will have a helical silica that can be used for various asymmetric organic synthesis. You can also generate a helical structure from achiral molecules, the molecules that do not have chiral centers. An example here is a platinum complex, which has no molecular level chirality, but if you disperse in some of the solvents, you end up some luminescent gels. And if you look at these gels in electron microscopy image, you will notice that there are both M and P type of helix, or the right and left-handed helices. And in such cases, because they have no chiral center, you will eventually have equal amount of both the handedness. In organic chemistry, it's called enantiomers. So you cannot have one of them higher because there is a possibility that each of them have 50. You can enrich one of the form by adding a small chiral dopant. At molecular and macromolecular level, you can study these chiral structures and molecules using circular dichroism or optical rotatory dispersion experiments. However, most of the chiral organic molecule absorb in the UV region of the electromagnetic spectrum. And chiral optical response of majority of biological molecules is very weak in the visible region of electromagnetic spectrum. That means that we need high concentration or large volumes of these molecules or analyte to study very systematically. There are many ways we can overcome by this is using small dye molecules, organic dyes, which has absorption spectra in the visible region. However, it's fundamentally challenging because this is limited based on the solubility and the type of the molecule that can use. What about going beyond molecules and macromolecules and supramolecules? We look towards the colloidal level structure, even higher order structure, how to generate that structures and how to study that structures. For this, we can use nanoparticle, especially plasmonic metal nanoparticles. In this case, what I'm showing you is a gold nanoparticles having very nano size dispersity. In such nanoparticle, we can confine light, and there are also enhanced light matter interactions. And nanoparticle also have optoelectronic properties that can be tunable based on the particle size, shape, surfactant, and the composition. And they can, if you are able to arrange this nanoparticle on a chiral object or structure, it will dramatically enhance the optical response. That means that we can lower the detection limit. It's not only lowering the detection limit, nanoparticles are also excellent building blocks for optical metamaterials, particularly gold if you use because it's highly stable and they are non-toxic. It's also biologically highly relevant. Even more interesting is that depending on the size, shape, and composition, we can also control the wavelength at which we can exploit this chiroptical response. For example, if we use gold, depth, size, and shape, we can cover visible, near infrared, up to mid-infrared region. That provides you an ample opportunity to use the same chiral system, but use different nanoparticles and study and develop optical metamaterials. And such materials are important as they open application in emerging circular polarizers, biosensors, asymmetric catalysis, and optically variable devices to detect counterfeit currencies and other objects. There are challenges because most of the existing methods to make this kind of helical structures are used nanolithography, but nanolithography is limited by producing small structures, but it's also challenging to produce genuine 3D morphologies. There's also a problem to scale them up. We can use wet chemical synthesis, but most of the methods are laborious, complex, and leads to non-uniform structures. For that, what we use is a superlattice formation. For those of you who don't know, superlattice is a periodic structure of layers of 2 or more materials. Typically, the thickness of one layer is a few nanometer to several tens of nanometer. It can be of 2 types of inorganic material, 2 types of organic inorganic, or any other combinations. And finally, after making these structures, what we look into is determining the structure. We can study using a variety of spectroscopic methods. We can use scattering methods, but to visualize the structure at really high resolution, even at sub-nanometer level, we look into cryo-electron microscopy if it's a bio-based structures, and we do the reconstruction, and that we call electron tomography. Electron tomography refers to collecting the lower dimensional structures and using a series of lower dimensional structures to construct higher order structure. If I have a series of 2-dimensional structures, and then I can do a 3D reconstruction. So in electron tomography, we have a series of 2-dimensional structures. As here I show, it's only 2D projections of a nanoparticle assembly. We collect many images at different angles. By tilting the sample, we combine them together and get the 3-dimensional structure. And here's a video showing the entire process, what we do. We collect about 70 images, stitch them together, and then do a mathematical construction. using high-end computational power. And we can look into the internal structure, and we can virtually slice this sample, and we can get detailed information about how each and every single nanoparticle is arranged. And we can determine the packing pattern of this. So the biotemplates that we use is, one of them is tobacco mosaic virus. It's a rod-like virus particle which has negative surface charge. It's about 300 nanometer in length, and it has 18 nanometer in diameter. It's made up of more than 2,000 small capsid proteins, capsomeres, which are arranged in helical fashion. And other biotemplate that we use is a DNA origami. It's an architecture that you can create by simply using what we call as a scaffold of DNA and staples. If you anneal them together, you can fold this scaffold, and you can also create crossover between them, and you can create the architecture that you want. And then it can result in this kind of hexagonally packed or closed cubic packing structures. Here, each rod, cylinder-like structures represent one of these double-stranded DNA structure. So we use 3 to 4 different types of DNA origamis as a biotemplates. And here I'm showing you 6 helix bundle, which means that this has 6 strands or helices, and it's about 400 nanometer. And here is a TM image of a 60 helix bundle, which only differs in the length and the height, and it's about 30 nanometer and 20 nanometer in width and 20 nanometer in height. And then we can also use a plate-like structures. And the formation of this structure is very well developed, and this can be followed using gel electrophoresis. For example, if you have only scaffold, you will see electrophoresis here. If you have only staples, then they end up here. But when you mix up them and you form, for example, here 60 helix bundle, you can see in the gel electrophoresis. So all these biotemplates have negative charge, and we use then cationic counterpart to make what we call as electrostatic assembly. Specifically, we use cationic gold nanoparticles, which are spherical, and they have very narrow size dispersity, and they're water dispersible and stable. And as a long chain cationic termination, we change only the core diameter. And as you can see, the size dispersity is rather narrow, and they're very stable if you keep them in the water. Here's a surface plasma resonance spectrum of this gold around 520 nanometer at immediately after synthesis and after 20 hours. Now, because electrostatic assembly, when you mix a cationic and anionic object, it generally results in a random aggregation, and irreversible random aggregation, and lead to what we call as kinetically trapped structures. Now we have to avoid such structure formation, and then we decided to approach it differently. If you take cationic particle and add some electrolytes such as sodium chloride, salt solution, they start to aggregate, but these aggregates are reversible. If you dilute the electrolyte concentration, then you can disassemble into individual nanoparticle. If you increase the electrolyte concentration, then you start to make them aggregates. So what we do here is that we use high salt concentration, nanoparticles are aggregated, then we add our rod-like biological templates, which are anionic. Now there is no immediate structure formation. Then we decrease the ionic strength. It means that dilute the concentration of sodium chloride by dialyzing this whole mixture against water. Then it starts to release individual nanoparticles. These nanoparticles now go one by one and arrange, and this leads to more controlled assembly. We study using numerous methods, but here as in a visual appearance, I'm showing you how we can control the structure formation using the ratio of nanoparticle and TMV. Here it shows that ratio of nanoparticle and TMV is 0.51. We go up to 500. But an optimal concentration we found that from nanoparticle to tobacco mosaic virus is 10, between 10 to 25. And if you take one of these and then you start to decrease the ionic strength, here is high salt concentration. You don't see any assembly formation because if you look at excess gold, the color is still same. But the moment you start to decrease the ionic concentration, you start something precipitated out. And this suggests that there is a colloidal level aggregate. And you can study these solutions quickly using, and the solution state, if there is some assemblies, using small angle X-ray scattering. And all these samples that we studied shows that there is a nice diffraction peak. That means there are some structures formed irrespective of the ratio. And however, the best diffraction peaks were observed only in the range of 10 to 25. So we try to look into it more detailed in electron microscopy. Here is cryo-electron microscopy image of this. What you see is that ratio is only 1. In this case, you see this higher order structure already, but you see a lot of free tobacco mosaic viruses, these rod-like structures here. But we also see some incomplete structures. And this type of structures are visible even if you go the ratio even higher. This suggests that irrespective of the ratio, we see some of the higher order structure in all samples. As we move on higher gold nanoparticle, then we end up having more and more but the final structure. So now we wanted to look at it in more detail, like really how these structures are formed, what is the mechanism. So we did some concentration dependent cryogenic electron microscopy imaging. And if you look in the very beginning, what you see is that two tobacco mosaic virus rods and intercalated with a few metal nanoparticles. You go again at a higher concentration, you start to see more and more intercalated structures. And finally, it leads to higher order structure. Many of these will merge together, form superlattice. And it's interesting what's happening is that we hypothesize first a nanoparticle will be attracted at low concentration, but this brings the two tobacco mosaic virus particles together. And then because it becomes already aligned, it becomes a nucleation center for other nanoparticle to come and attach. And then finally, you start to see. So irrespective of the amount, it is not a random aggregation. The first nanoparticle attracted to a virus particle will start to nucleate. And we call this as a zipper mechanism. It's an analogy to the zip that the previous structure will be important to make the more complete structure as you move forward. This is exactly what happens in this case. However, there is something more surprising or unexpected result, because if you take any rod-like particle, if you assemble them, a commonly observed packing is hexagonal close packing. However, the small angle X-ray scattering says that we don't have a SCP packing, but instead there is a 2D array of superlattice. And this 2D array equal to 2D square lattice. Now it is very difficult to suggest why this pattern is observed. And for that, we look into what's called electron tomography. Here is a large structure of this wire. As you can see already here, some helical twist. But we look into a little bit more detail. We first collect the tilt series, and the twist is very clearly visible. Then we reconstruct this and look into more detail. As mostly you see here nanoparticle, you cannot see the virus rods because of the contrast difference between the gold and the biological molecules. And then you can go even more further and identify each and every single gold, the 3D coordination of every gold atom. From this, we can extract even more details. And this now suggests that why and we really have a 2D square lattice. And this information and extraction of three-dimensional coordination from this also assists us to understand why we see the helical structure. because now we can use this information to simulate and even extrapolate and computationally simulate the structures and understand the growth of these helical colloidal superstructures. But it is possible now to suggest why exactly we have the square lattice. It has to do with the ratio of the diameter between the metal nanoparticle and the virus nanoparticle. But since we have variation only in gold core that can be done, so we change different types of nanoparticle, all cationic of different size. The original nanoparticle was about 15 nanometer. So we went down to 5 nanometer and 8 nanometer particle. And at that stage, we start to see the hexagonal close packing as the small angle X-ray scattering suggests. Then we move to DNA origami nanoparticle superlattice, how it works. The interesting thing compared to virus nanoparticle is that DNA, we can have different structures. So here we can do variation both in the biotemplate and also nanoparticles. So we can study not just the variation of nanoparticle size, also biological template, unlike in virus case. And that is the main motivation to move towards DNA origami structures. Interestingly here, it's a 6-helix bundle, which is a long 400 nanometer rod-like structure. When we use small 8.5 nanometer particle, we start to see square lattice, not hexagonal, but we observed no real structure or well-defined structure around a larger nanoparticle. But if you move to even higher structure, then we start to see hexagonal structure. And if you go to 24 helix bundle, it has square lattice in all 3 nanoparticle clearly visible. And 60 helix bundle, square at large nanoparticle and extra large nanoparticle, we will also have square lattice. So it's really interesting that we can tune the packing pattern depending on the size and shape of nanoparticle, at the same time also biological template. And here is the cryo-electron microscopy image where we can see is a large bundles of these structures. We can go further and look into, for example, arrangement of each nanoparticle, which is very clearly visible here. For example, in this, depending on which axis we are viewing, and more detailed structure can be obtained if you look at inverse Fourier transform of this electron microscopy image, where we can see clearly it's an hexagonal packing. But if you see slightly a different viewing axis, then you start to see this the rectangular or square lattice structure. But it depends on the nanoparticle and the template that you use. Here is electron tomography, from which we can extract the location of the nanoparticle, and then we can create a model to suggest the actual packing of the structures. So what we do is that we create structures, we study, and then we do a microscopy, small angle X-ray scattering, and circular dichroism, and then do eventually the reverse engineering to propose the structure based on the experimental evidences. But gold nanoparticles, we can only move to a certain range of wavelength in the electromagnetic spectrum. So instead of gold nanoparticle, if you move to gold nanorods, they are anisotropic. We can move towards the NIR region. Here is an example of cationic gold nanoparticle. We have same functionality, and these gold nanorods have about 30 nanometer in length, 10 nanometer in diameter, so aspect ratio of roughly 3, and it has a nice SPR spectrum centered around 800 nanometer. And now the idea is simple. How happens if you take, instead of spherical, if you keep 2 rod-like nanoparticles. And this is what is proposed and expected. But what happened in this case is that we also see helical structures even more bigger. And we saw about 500 nanometer in virus nanoparticle case. Here we start to see really a micro and macro wires, really several micrometers. As you can see, the length scale is here 10 micron. So, and large helical structure. So we are not only changing the nanoparticle, but also we are moving to another length scales here. And it's also beautiful because we can now start to see a nice NIR chiral plasmonic structures. And also from electron tomography, we can provide evidence that it has a right-hand helical structure. With this, I would like to summarize what I have been presenting is biological nanoparticles are good templates if you want to exploit them for chiral superstructures. They allow electrostatic assembly because naturally they have a rich surface chemistry. We can use surface modified nanoparticles. The finer structure, packing, and properties can be tuned by controlling the template architecture, as we have shown, for example, in DNA origami, or metal nanoparticle size and shape. As for example, if you want to move different part of the electromagnetic spectrum, we can go from spherical to anisotropic nanoparticle. So combining biological particle with metal nanoparticle offers routes for chiral plasmonic superstructures across different length scale. And it often results, as we have shown, the square-like formation, which completely unprecedented assembly. However, like in any other work, there are numerous limitations for this work. Biological particles are excellent template, but unfortunately they are delicate. They are sensitive to environmental conditions. You need to have very controlled condition to work with them. Electrostatic assemblies, irrespective of whether it's controlled or random, they result in rigid structures. Therefore, they're mechanically weak. So handling them is really challenging. Scalability and making large scale and long-term